Thanks for the introduction. Yeah, we're talking about many things, but mostly digital building regulations and how to make them, because they're necessary for this thing that we call compliance checking, which is, I would say, the interface of the domain of building information and the domain of normative knowledge. And as I work in the semantic web and in building data, that would practically mean that on the one side we have this building information models, which are graphs. And on the other side, we have the normative knowledge that we try to serialize as SHACL shapes, which is a constraint language that we can use to check the graphs. And then what happens in the middle in the compliance checking thing is we basically check whether these two match, right? Which is an ontology-driven process. So we need semantics or ontologies that bridge the two knowledge domains. The challenge that we try to tackle in this paper is generating this thing, because most of our regulations are text-based and not SHACL-based. And what we try to do is, can we combine symbolic knowledge representations, such as ontologies, and neural AI, such as LLMs, to convert the text-based regulations that we have into these SHACL shapes. We have a couple of principles. We want to limit the cost of LLM usage. So we use massive ontologies. If we load them in the context, then we will simply have too many tokens. We want to enable automatic and human validation of the SHACL shape, and we want to be ontology driven throughout the entire pipeline. So the methodology and maybe also the results, and I will go through this step by step, is this pipeline. So let's just start. We have a regulatory statement, which is a text-based thing. So for example, a fire compartment cannot exceed 2,500 square meters. On the other side, we have an LLM. And what we first try is relatively old school NLP stuff. So we extract the individual tokens from the sentence and we do noun chunking, which we then join as features and load into the LLM together with the original textual sentence. So that NLP stuff, for example, does this. So we have, as the beginning of a sentence, a portable fire extinguisher. And what we want is to chunk this into one thing, so that if we then later on do semantic mapping and trying to match this with an ontology, that we don't match the individual word fire or the individual word portable, but the entire thing, right? Then we have ontologies. So we use a domain ontology, which is, in this case, a fire safety ontology, because we're doing fire safety regulations. And we have a couple of W3C link building data ontologies, so that just let's say the core ones, so bot and BEO, etc. As I explained, these are very big. What we first do is we make a table with just the label and the definition of it. So we have a list with terms and what they mean. But if we would load this in the context, that would explode the thing. So what we try to do is we try to run a cosine similarity between these features, so a portable fire extinguisher and the ontology, to reduce the size of the ontology and kind of create a virtual ontology that matches this single regulatory statement. So for example, on the one side, we have this feature, a portable fire extinguisher. On the other side, we have terms in the ontology. So the name and the definition, and then we run this cosine similarity between all the terms. We take the 10 best ones, and then this is our virtual or optimized ontology, which we can then load into the LLM. Then the other thing we load is shape instructions. So the LLM doesn't exactly know how we want to format the SHACL shape. So we try to give instructions, for example, by giving example shapes, patterns on how to model certain things in SHACL, and also instructions how to do first order logic to SHACL mapping. We'll get to that later. This is one of these example templates that we, for example, give to the LLM. So here we, for example, show how it should deal with requirement and exception logic and how to model that in a SHACL way, because there's multiple ways of modeling it. And it should match the modeling principles of our link building data of the graph. So we load these things. Then we create multiple tasks for the LLM. So first it makes a mapping table between these words, the features, a portable fire extinguisher, and the terms from this optimized ontology. We then use these words to make a first order logic representation of the regulatory statement, and this we convert to SHACL. And the result is, for example, one of these shapes. So this on the right side is a SHACL shape that was converted by the pipeline, and it contains in the top box this SH message, which is the original textual regulatory statement. Then it creates the first order logic representation of that statement. And the rest is a machine executable code, which is the SHACL thing. And we did not invent the structure from scratch. So it maps to, for example, this race tagging mechanism. It also maps to antecedent consequent logic. So you can see similarities with previous research. And then what we finally do is we have on the right bottom, shape evaluation. So we want to evaluate the SHACL shape because fire safety experts in our case need to use it. And we have a couple of methods. We tried regex-based methods where we check for like syntactical SHACL elements. So if they're not present, then the shape will not work. So they have to be there. We also check for ontology prefixes so that they are correct and the LLM does not invent new ontologies on the fly. We have human experts selecting terms. For example, a specific section about fire compartments needs to have this specific word from the ontology. So we can also check for this. And we built this rule-based SHACL to diagram or mermaid converter. So this representation that you see on the right is the same thing as in our previous slides, but then in a human readable format. So the human expert can now kind of see the decision logic that the SHACL shape goes through and then check whether that's similar to what they would do and either agree with it or disagree, and then we run the algorithm again. So we tested this on Dutch building codes. We tested this for regulations in multiple categories, such as information availability, value checks, relational checks, mathematical checks, and conditional checks. The results are super nice. So it was able to make relatively complex SHACL creations or so. So it would, for example, understand exceptions and even nested exceptions and model them properly because it has these template shapes. And what we did to evaluate is we had data graphs. So we kind of BIM information, but then in a graph-based format that we made manually, and we manually made some errors based on the regulation. So this thing contains 5 zones, but the regulation says that it should only contain 4. The sum of the areas is 1200, while the regulation says it can only be 1000. And then we ran this in a SHACL validator, this generated SHACL shape to see whether it would actually track those. And it did. So it was able to create these compliance reports that have both a human readable message stating what is wrong, but it's also machine readable. So it also points to this thing called focus node. So the exact thing in your link building data graph that does not comply with the regulation. Is this finished work? Far from. There's many things that we could or should improve. In this Neuro-Symbolic pipeline, we use this RDFS label and comment, so the name and the description of a class, but there's way more logic in the ontology in OWL that we might use, and I don't know how, but that's something to explore. We cannot yet deal with external sources. Often regulations point to I don't know, NAND norms or ISO norms or something that we cannot access always, so that's difficult. With the cosine similarity, we created this optimized ontology or virtual ontology with n is 10, which is super arbitrary and it might not work for more complex regulations. Maybe it's too much, maybe it's too little, I don't know. And SHACL is also a difficult format. It's binary, so it operates in a closed world assumption, but semantic web is open world assumption. This is very difficult. So I mean, there's things to improve, but we're on the way. So my conclusion would be that I think that symbolic knowledge representations such as ontologies can help neural AI to generate better SHACL shapes, but we need more research to, for example, combine with the VLM work that we saw yesterday to do more complex regulations, also more combinations of multiple regulatory statements, etc., etc. And that's where I'd like to thank you and leave it.